Welcome to this coding tutorial. Today, we'll dive into problem number 399, Evaluate Division. This is an interesting graph-based problem where we compute values for division queries based on given equations and values. Let's explore the approaches and techniques to solve this step by step. In this problem, you are tasked with evaluating division queries based on given equations and their corresponding values. Each equation is expressed as a pair of strings, where the first string divided by the second string equals a given numeric value. For example, the equation a/b equals k means that dividing a by b results in the value k. Your goal is to compute the results for a series of division queries, which are also expressed as string pairs, like x/y. If a query cannot be resolved due to missing information or disconnected variables, you should return -1.0 as its result. To summarize the input, you are provided with a list of equations, their corresponding values, and a list of queries. The output will be a list of floating point numbers representing the results of the queries, or -1.0 for those that cannot be computed. Now, let's consider an example to better understand the problem. Suppose we have the equations a, b, b, c with values 2.0, 3.0. This means a/b equals 2.0 and b/c equals 3.0. The queries are a, c, b, e, x, x. For the first query, a/c, we can combine the given equations, a/b equals 2.0 and b/c equals 3.0, resulting in a/c is equal to 2.0 times 3.0 equals 6.0. For b/a, we know a/b equals 2.0. So b/a is the reciprocal, or 1 divided by 2.0 is equal to 0.5. For a/e, since e does not appear in the equations, the result is -1.0. For a/a, any variable divided by itself is 1.0. Finally, for x/x, since x is not part of the equations, the result is -1.0. The output for this example is 6.0, 0.5, -1.0, 1.0, -1.0. Let's look at another example. Here, the equations are x1 is x2, x2, x3, x3, x4, x4, x5, with values 3.0, 4.0, 5.0, 6.0, and the queries are x1, x5, x5, x2, x2, x4, x2, 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 x9, x9, x9. For x1/x5, we multiply all the given values, x1/x2 equals 3.0, x2/x3 equals 4.0, x3/x4 equals 5.0, and x4/x5 equals 6.0. Combining these, x1/x5 is equal to 3.0 times 4.0 times 5.0 asterisk 6.0 is equal to 360.0. For x5/x2, we take the reciprocal of x2/x5, which is 1 divided by 360.0 almost equals 0.008333. For x2/x4, we combine x2/x3 equals 4.0 and x3/x4 equals 5.0, resulting in x2/x4 is equal to 4.0 times 5.0 equals 20.0. For x2/x2, any variable divided by itself is 1.0. These calculations align with the corresponding outputs. For the remaining queries, x2/x9 and x9/x9, we notice that x9 does not exist in the equations. When a variable is not part of the given data, the result for its division is -1.0. This applies to both x2/x9 and x9/x9. To summarize the constraints, the number of equations in queries ranges from 1 to 20, and the values in values are between 0.0 and 10,000. Additionally, variable names are non-empty strings of up to 5 characters consisting of letters and digits. Division by zero is guaranteed not to occur, and the graph formed by the equations is acyclic. These constraints ensure the problem remains well-defined and computationally feasible. To solve the evaluate division problem, we can think of it as a graph problem. Here, the variables act as nodes, and the division relationships between them form directed edges with weights representing the division values. We explored several approaches. The first approach is the brute force method, where we directly evaluate each query by testing all possible paths between the two variables. This involves using recursion or depth-first search to explore connections. However, this method has a high time complexity, growing factorially with the number of variables, making it infeasible for large inputs. While simple to implement, it's computationally expensive and not practical for most scenarios. The next step builds on this idea by explicitly representing the relationships as a graph and using depth-first search to traverse it more systematically. Building on the graph representation, we can use DFS to evaluate division queries. In this approach, we first construct the graph using adjacency lists, where the nodes represent variables, and the edges carry weights corresponding to the division values. To answer a query, we perform a depth-first search starting from the numerator variable, exploring possible paths to the denominator while keeping track of visited nodes to avoid cycles. If a path exists, we calculate the result by multiplying the weights along the path. This method is much more efficient than brute force, with a time complexity of O, Q asterisk, V plus E, where V is the number of variables, E is the number of equations, and Q is the number of queries. Another option to consider is BFS, which explores the graph layer by layer. This ensures that the shortest path between nodes is found first, which can be advantageous in certain graph structures. Like DFS, BFS also builds the graph and traverses it to compute results for the queries. An alternative and highly efficient approach is to use the union-find data structure, also known as disjoint set union. This method involves grouping variables into connected components while maintaining information about their relative ratios. For each query, we check if the numerator and denominator belong to the same connected component. If they do, we compute the result using the stored ratios. Otherwise, we return -1. The process includes constructing the union-find structure, grouping variables, and storing their relative values. This approach has an impressive time complexity of O, E plus Q, asterisk alpha V, where alpha is the nearly constant inverse Ackermann function, making it highly efficient for large datasets. However, it requires careful management of parent pointers and ratios, making it somewhat complex to implement compared to DFS or BFS. For this problem, we have chosen the graph representation with DFS as the primary approach. This strategy maps naturally to the problem structure, with variables, equations, and queries corresponding to nodes, edges, and paths. The transitive nature of division relationships, where A/B equals X and B/C equals Y imply A/C equals X asterisk Y, is perfectly suited for graph traversal. A directed graph with weighted edges allows us to model and compute these relationships efficiently. While union find is more efficient for very large datasets, DFS is simpler to implement and sufficient given the constraints of the problem. It eliminates the need for additional data structures, reducing complexity while maintaining clarity and effectiveness. Each approach comes with trade-offs. DFS is straightforward to implement but may be slower for graphs that are deep or highly connected. Union find, on the other hand, is more efficient but introduces implementation complexity due to the management of parent pointers and relative ratios. BFS is similar in complexity to DFS but requires more memory due to the queue used in traversal. Ultimately, the graph-based DFS approach strikes the right balance between simplicity and efficiency. It offers a clear and intuitive way to model the problem and performs well within the given constraints. For larger datasets, union find could be considered as an optimization, but for typical scenarios, DFS provides a reliable and practical solution. The evaluate division problem can be thought of as a graph problem where variables are represented as nodes and division relationships as edges. Each edge is weighted with the division result, such as S/B equals 2.0, which means there is an edge from A to B with a weight of 2.0. Likewise, the reciprocal relationship is also modeled, so there's an edge from B to A with a weight of 1/2.0. The task is to compute division queries like A/C by determining if a path exists in this graph between the nodes. To start solving this, we model the problem using an adjacency list. Each variable acts as a key, and its neighbors are stored in a nested dictionary where the weights represent the division results. This graph structure will allow us to efficiently store and access data for the given equations, setting up the foundation for solving the queries. Once the graph is constructed, the next step is to answer the division queries by performing graph traversal. For a query like A/B, we first check if both variables exist in the graph. If either variable is missing, we return -1.0, as no relationship exists. If the variables are the same, the result is 1.0 because any variable divided by itself equals 1. To find relationships between variables, we use depth-first search, which explores the graph to search for a path from the start variable to the end variable. During this traversal, we maintain a running product of edge weights to calculate the result dynamically. To prevent revisiting nodes and forming infinite loops, we use a visited set. If a valid path is found, the accumulated product is returned, otherwise, we return -1.0. This approach also handles edge cases such as disconnected components, self-loops, and invalid queries involving non-existent variables. Using this strategy, we can efficiently navigate the graph to handle both forward and reverse queries thanks to the reciprocal edges added during graph construction. The visited set ensures that cycles in the graph do not lead to infinite traversal, while the adjacency list representation provides quick access to neighbors, making the approach both space-efficient and practical for sparse graphs. The DFS implementation uses recursion, leveraging the call stack to dynamically compute results during traversal. In terms of performance, building the graph from the equations takes time, where E is the number of equations. For each query, the DFS exploration takes V plus E, time in the worst case, where V is the number of variables. If there are n queries, the overall complexity becomes V plus E, making this method scalable for large inputs. To illustrate how the algorithm works, let's walk through an example. Given the equations a/b equals 2.0 and b/c equals 3.0, we first construct the graph. From the first equation, we add an edge from A to B with weight 2.0 and a reciprocal edge from B to A with weight 0.5. From the second equation, we add an edge from B to C with weight 3.0 and a reciprocal edge from C to B with weight 1/3. The resulting graph is represented as A connects to B with weight 2.0, B connects to both A and C with weights 0.5 and 3.0 respectively, and C connects back to B with weight 0.333. Now, let's execute the queries. For A/C, we perform DFS starting at A and find the path A-B-C. The product of the weights along this path is 2.0 times 3.0, resulting in 6.0. For B/A, the path is B-A, and the result is 0.5. For A/E, since E is not in the graph, we return -1.0. Finally, for A/A, we return 1.0 because a variable divided by itself equals 1. For the last query, x/x, since x does not exist in the graph, the result is -1.0. The final outputs for all the queries are 6.0, 0.5, -1.0, 1.0, -1.0. This example highlights the efficiency of our graph-based approach in handling various scenarios, including valid queries, self-loops, and cases where variables are missing. By combining graph modeling, DFS traversal, and careful handling of edge cases, we can systematically solve the evaluate division problem with precision and scalability. Here, we start by importing the necessary modules. We use defaultDict to easily create a graph representation of the equations, and Deque for efficiently handling the breadth-first search, BFS, traversal. The calc equation function begins by constructing the graph as an adjacency list. Each equation is processed such that the numerator and denominator are connected, with the given value representing the weight of the edge between them. Additionally, we add the reciprocal relationship, connecting the denominator back to the numerator with the inverse of the value. This ensures the graph is bidirectional and correctly represents all relationships. Next, we define a helper function, BFS, which will handle the traversal to evaluate division queries. The first step in BFS is to check if both the starting and ending nodes exist in the graph. If either is missing, we return -1.0 to indicate that the division is not possible. We also handle the simple case where the start and end nodes are the same, immediately returning a value of 1.0 because any variable divided by itself equals 1. Then, we initialize a set to keep track of visited nodes and a queue to manage our BFS traversal. The queue starts with the start node and an initial product of 1.0, representing the cumulative result of the division so far. The BFS traversal continues by processing nodes from the queue. For each node, we check if it matches the end node. If it does, we return the current product, which represents the result of the division. Otherwise, we mark the current node as visited and explore its neighbors. For each neighbor, we check if it has not been visited yet. If it hasn't, we calculate the new product by multiplying the current product with the weight of the edge to the neighbor, and then add the neighbor to the queue along with this updated product. If we exhaust all possibilities and never reach the end node, we return -1.0 to indicate that the division is not possible. Finally, outside the BFS function, we process each query in the queries list using our BFS traversal. For each pair of variables, start and end, we invoke BFS and collect the results in a list, which is returned as the final output. This ensures that each query is efficiently handled and the results are computed accurately. Here, we start by defining the method calc_equation, which takes three inputs: a list of equations, an array of corresponding values, and a list of queries. The goal is to evaluate each query by determining the division result based on the given equations. To achieve this, we first construct a graph represented as an adjacency list, where each node corresponds to a variable, and each edge has a weight representing the division value between two variables. Inside the loop, for each equation, we extract the numerator and denominator, as well as the associated value. We then ensure both variables are present in the graph by initializing their adjacency maps if they aren't already. Next, we establish the bidirectional relationship between the two variables. For example, if numerator/denominator equals value, we record this in the graph, and we also add the inverse relationship, denominator/numerator equals 1.0/value. This step ensures that our graph is properly built and ready for traversal. Finally, we define a helper function BFS to perform a breadth-first search, which will help us evaluate the queries. The BFS function is used to calculate the result of a division query. First, we check if the graph contains both the starting and ending variables. If either is missing, we return -1.0, indicating that the query cannot be resolved. If the start and end variables are the same, the result is simply 1.0, as any value divided by itself equals 1. After these initial checks, we set up the BFS traversal. A visited set is used to ensure that we do not revisit nodes, and a queue is initialized with the starting variable and an initial product of 1.0. The queue stores pairs of variables and their cumulative product values. While the queue is not empty, we retrieve the next pair. If the current node matches the target variable, we return the product as the result of the query. Otherwise, we mark the current node as visited and explore its neighbors. For each unvisited neighbor, we calculate the cumulative product by multiplying the current product with the edge weight and add this neighbor to the queue. If the queue is fully processed without finding the end variable, we return -1.0, indicating that the target is unreachable. To process the queries, we iterate over the list of queries using a for loop. For each query, we extract the start and end variables, then invoke the BFS function to compute the result of the division. The result is stored in the results array at the corresponding index. Once all queries are processed, the method returns the array of results. Additionally, we define a helper class pair to store a pair of values, specifically a variable and its associated cumulative product during the BFS traversal. The pair class includes getter methods for accessing the key and value, ensuring a clean and modular implementation. This structure allows us to efficiently manage the variables and their associated values while traversing the graph. With this implementation, we can handle multiple queries and dynamically evaluate division results based on the given equations and values. To begin solving this problem, we first need to build a graph representation of the input equations. The equations provided are a/b equals 2.0 and b/c equals 3.0. Using these, we construct an adjacency list where each node is connected to its neighbors with a weight representing the division relationship. For instance, A connects to B with a weight of 2.0, and B connects back to A with a reciprocal weight of 0.5. Similarly, B connects to C with a weight of 3.0, and C connects back to B with a weight of approximately 0.3333. With the graph built, we now use breadth-first search, or BFS, to evaluate the queries. This allows us to find the product of weights along a path between any two nodes, if such a path exists. Now, we start evaluating the queries using BFS. For the first query, A/C, we begin at node A with an initial product of 1.0. From A, we visit its neighbor B, updating the product to 2.0. Then, from B, we visit C, further updating the product to 6.0. Thus, the result for A/C is 6.0. Next, for the query B/A, we start at B with a product of 1.0. Moving to its neighbor A, we update the product to 0.5, which gives us the result of 0.5. For A/E, since node E does not exist in the graph, the result is -1.0. Similarly, for A/A, as the start and end nodes are the same, the result is 1.0. Each node divided by itself will always yield 1. Finally, for X/X, as node X does not exist in the graph, the result is also -1.0. With all the queries evaluated, the final output for this example is 6.0, 0.5, -1.0, 1.0, -1.0. Now, let's consider the second example, which introduces disconnected components. The input contains two separate equations, A/B equals 1.5 and C/D equals 2.5. Using these, we construct the graph. A connects to B with a weight of 1.5, and B connects back to A with a reciprocal weight of approximately 0.6667. Similarly, C connects to D with a weight of 2.5, and D connects back to C with a reciprocal weight of 0.4. Notice that there are no edges connecting the components A, B, and C, D, making them disconnected. To evaluate the queries for this example, we again use BFS. For A/B, starting at A with a product of 1.0, we visit B and update the product to 1.5. Thus, the result is 1.5. For B/A, starting at B with a product of 1.0, we move to A and update the product to approximately 0.6667. This gives us the result 0.6667. For A/C, since A and C belong to separate disconnected components, there is no path connecting them, so the result is -1.0. Finally, for C/D, starting at C with a product of 1.0, we visit D and update the product to 2.5. The result is therefore 2.5. After evaluating all the queries in this example, we get the final output, 1.5, 0.6667, -1.0, 2.5. Now, let's examine a third example that includes self-loops and non-existent nodes. The input contains a single equation, x/y equals 4.0. From this, we build the graph where x connects to y with a weight of 4.0, and y connects back to x with a reciprocal weight of 0.25. This graph is straightforward as it only contains two nodes and one edge. For the queries in this example, we start with x/x. Since the start and end nodes are the same, the result is 1.0. Similarly, for y/y, as the start and end nodes are identical, the result is also 1.0. Finally, for z/z, node z does not exist in the graph, so the result is -1.0. The final output for this example is therefore 1.0, 1.0, -1.0. To analyze the time complexity, let's first look at graph construction. We build the graph as an adjacency list, where each equation contributes two directed edges, one from the numerator to the denominator and another in the reverse direction. If there are equations, this process takes constant time per equation, resulting in an overall graph construction time of O(e). Next, for BFS traversal during a single query, we initialize a queue with the starting node, which takes O(1) time. The traversal itself, in the worst case, visits all nodes and edges within the connected component of the graph. If there are n variables and edges, this traversal takes O(n plus e). Since BFS is performed once per query, the time complexity for processing one query is O(n plus e). Finally, if there are q queries, the total time complexity for all queries becomes O(q*(n plus e). Now, combining graph construction and query processing, the overall time complexity becomes O(e plus q*(n plus e). Shifting to space complexity, the graph is stored as an adjacency list. Each equation contributes two edges, so with e equations, the graph requires O(e) space. However, in the worst case, where all variables are interconnected, the adjacency list could grow to O(n²), since each node may connect to every other node. During BFS, additional space is used for the visited set, which stores all n nodes in the worst case, requiring O(n) space. The BFS queue also holds up to n nodes at once, contributing another O(n). When we combine graph storage and BFS space requirements, the total space complexity in the worst case is O(n² plus n). Now, comparing this graph-based approach to a naive method, the difference becomes clear. The naive approach would attempt to compute results for each query by iterating through all equations to find paths, leading to a time complexity of O, Q asterisk e to the power of k, where k represents the maximum recursion depth or path length. This involves significant redundant computation. On the other hand, the graph-based approach avoids such inefficiencies by using BFS to find paths efficiently. Since adjacency lists ensure that edges are traversed only once, the graph-based approach reduces the time complexity to O, E plus Q asterisk, N plus E, making it much more scalable for larger graphs. Finally, let's consider the best, average, and worst-case scenarios. In the best case, the graph is sparse, and each query involves nodes within small connected components. Here, BFS traversal is minimal, and the time complexity approximates O, E plus Q. For the average case, in moderately connected graphs, BFS processes a subset of nodes and edges for each query, maintaining the time complexity at O, E plus Q asterisk, N plus E. In the worst case, with a dense graph and many queries, BFS may explore all nodes and edges for each query, but even here, the complexity remains O, E plus Q asterisk, N plus E. This analysis highlights how the graph-based approach performs consistently across different scenarios while optimizing for scalability. When tackling this problem, there are some common mistakes to watch out for. First, it's important to avoid misinterpreting the problem as a direct calculation task. While it might seem like simple arithmetic, the real challenge lies in modeling the relationships as a graph and solving it as a pathfinding problem. Overlooking this can lead to inefficient or incorrect solutions. Another frequent mistake is forgetting to handle disconnected nodes. If two variables are not connected in the graph, their queries should return -1.0, so failing to account for this will result in inaccurate outputs. Additionally, using a depth-first search without cycle detection is risky. If your graph has cycles, a naive DFS can lead to infinite recursion or produce incorrect results, so marking visited nodes properly is essential. Lastly, be mindful of floating point precision issues. Division operations can sometimes introduce small inaccuracies, so comparing results with a tiny epsilon value can help prevent these bugs. Now, let's look at inefficiencies in graph traversal and how to optimize for multiple queries. A common issue is recomputing paths for every query with DFS or BFS, which can be quite inefficient, especially with many queries. This approach has a time complexity of O, Q asterisk, N plus E, where Q is the number of queries, N is the number of nodes, and E is the number of edges. Instead, using a pre-computed transitive closure, such as the Floyd-Warshall algorithm, can significantly speed up query resolution by pre-processing all pairs relationships. From an interview perspective, there are a few things to keep in mind. First, always clarify how the graph should be represented based on the problem constraints. In most cases, an adjacency list with edge weights suffices. Second, while union find is a great alternative for determining connected components or equivalence relations, it's less intuitive for handling weighted graphs. Third, remember to treat the division values as edge weights. For example, a/b equals 2 translates to an edge with weight 2 from A to B and a reciprocal weight of 0.5 from B to A. This bidirectional symmetry is crucial. Finally, for scenarios involving many queries, pre-processing with algorithms like Floyd-Warshall, which runs in O, n cubed, can save a lot of time later on. To deepen your understanding of this topic, it's helpful to explore related problems. For example, LeetCode 399 Evaluate Division is the foundational problem that introduces these concepts. LeetCode 684 Redundant Connection focuses on graph connectivity and cycle detection, which are essential for understanding how to manage relationships between nodes. LeetCode 990 Satisfiability of equality equations involves determining equivalence relations, often solved using the union find algorithm. Finally, LeetCode 743 Network delay time is another graph problem that deals with weighted edges and shortest paths, offering further practice in managing weights and graph traversal techniques. These problems build on the foundations of graph theory and provide valuable practice for both interviews and broader problem-solving skills. There are several alternative approaches to solving this type of problem, each with its own trade-offs. Using DFS or BFS traversal is often the simplest to implement, but it can become inefficient when there are many queries. Each query in this approach requires O, n plus E, time, so it's best suited for cases where the graph is sparse and the number of queries is small. The Floyd-Warshall algorithm, on the other hand, pre-computes all pairs' shortest paths in n³ time. While this pre-processing can be expensive in terms of time and memory, it allows for extremely fast query resolution later, making it ideal for dense graphs with a high volume of queries. Finally, union-find with path compression is an excellent choice for problems that focus on connectivity checks and equivalence relations. However, it's less intuitive for weighted graphs, as additional bookkeeping is needed to maintain edge weights. This approach is most effective when the problem revolves around determining connected components or equivalence relations, rather than detailed path calculations. Great job! In this session, we solved the evaluate division problem, explored graph-based techniques, and discussed their complexities. Keep practicing graph problems to strengthen your skills. Don't forget to like, subscribe, and stay tuned for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!